Alright, so we're going to walk through a way to solve a problem involving angular momentum with a collision between two objects. So in this problem, it's specified that a bullet's flying in at an unknown velocity and collides with this rod with a mass of 4 kilograms and a length of 0.5 meters. It gives us the equation for moment of inertia of the rod to be 1/12 mL squared, where L is the actual length in its entirety, not the radius from the axis of rotation. So that's an important component to make sure that we understand. So the second thing we need to do is we need to recognize kind of what the other component of momentum is. So we have an angular inertia, rotational inertia. We also have a velocity, or an angular velocity, omega. And so we know that our momentum is going to be equal to our angular inertia, or rotational inertia, I, times omega. But there are two objects that make up this total momentum. So let's talk about how we can find the total momentum of the whole system. So to start off with, what we want to make sure that we're doing is finding the momentum of the two objects combined, because it says that they are colliding together, the bullet's going to stick into that rod. So I'm going to say my total momentum is equal to the momentum of the rod plus the momentum of the bullet. And so here's the tricky part about these types of problems. When we see a bullet coming in, it looks like it's moving in a straight line and it only has a translational component. It doesn't have an angular velocity. It's not spinning, it's not rotating. But as soon as it begins to start to interact with this rod, even right before it starts to interact with the rod, technically what we're saying is it's going to become a point mass that's rotating about this axis. So we do give it an angular velocity. We can convert that translational velocity v into an angular component. And so here's what we're going to look at now. We're going to say that we know that the total momentum is the inertia of the rod times the velocity of the rod plus the inertia of the bullet times the velocity of the bullet. And luckily, we have angular velocities of the rod and bullet. Both of them are in this rod moving at 10 radians per second, so we already know the velocity for both of them. And then we can calculate the moment of inertia, or the rotational inertia for each object. So we can say it's 1/12 L squared, times that inertia plus mr squared times that velocity. I think I might have said inertia here. I meant to say velocity. So it's inertia times velocity plus inertia times velocity, or the momentum of each object. And we can't just kind of lump the mass of the bullet into the rod's mass equation or the rod's inertia equation, because by embedding itself, it changes its actual kind of coefficient and the way that the mass is distributed. So we just treat them as two separate objects and add them together after that. And when we do that, we know all these values now, making sure that L is actually 0.5 in this case, and R is 0.25, because this is from the axis of rotation, whereas this L is the full length here. We should get a value that is equal to 0.835. And the unit for this is kind of a little bit odd. We're doing a kilogram meter squared radian per second. So it's just all the units that we have multiplied together. So it's a kilogram meter squared radian per second. Boom. Now, what is the next component that we're looking at here? Well, we need to figure out what the velocity of the bullet was just before impact. So let's jump over to this section here. The velocity of the bullet just before impact. We're going to say that the bullet, or we know that the bullet is entering at an angle. So any velocity that we find now is going to only be this parallel component. That's the velocity that we're going to actually be able to find. Any velocity that was part of this component is going to be lost. It's not actually going to make up a portion of the velocity that's going to solve the problem for us. So let's first consider the perpendicular momentum. We know that our total momentum was 0.8351, and so all of that momentum had to come from the bullet, because in the problem it specifies that the rod was actually stationary. The rod was stationary before the collision. So we're going to take that bullet and we're going to say, well, the total momentum is equal to the inertia of the bullet times the angular velocity of the bullet. Now again, it's tempting to say, well, the bullet didn't have any angular velocity. It's moving in a straight line here. But remember, the instant it's about to interact with this rotating rod, we can convert its velocity into an angular velocity. So we can say that instead of I of the bullet, omega of the bullet, we can say that that's mr squared times, now instead of the angular component, we're only going to get the actual translational component, and so we can convert that into velocity over radius. And it actually ends up being m, the radius squared component cancels out here with this radius, so it's m times radius times v. And so we can say that's equal to 0.8351. This is the mass of the bullet, and this is the radius where it's hitting, which is 0.25. And when we solve for that, we get a significantly large velocity. But here's the trick. Remember, we only found that perpendicular component of velocity. So what we need to be able to do is say that this is a v perpendicular, right? But we need to find this component, where this is actually 30 degrees, because this is 60 degrees. So we can say that cosine of 30 degrees, make sure your calculator's in degrees for this component, because it's 30 degrees, not 30 radians. Cosine of 30 degrees is v parallel over v, and the hypotenuse is the component that we're actually looking for here. And when we solve for that, we end up getting a total velocity. The hypotenuse velocity value is going to be 1,285.8. Okay, so now we've got two parts here. The last thing we need to do is we want to figure out how much energy was lost during that collision. Because remember, part of what's happening here, first of all, it's an inelastic collision, so mechanical energy is not going to be conserved necessarily. And then second of all, it is a collision at an angle with a rotating object, meaning this parallel component actually does nothing to the rotation of the object. It doesn't apply any torque whatsoever. And so that's another area that we might be losing energy from. So to set up this problem, I know that my energy, let's pick out a different color here. I know that my energy initially is all from the bullet. My energy initially is all from the bullet, so that's just 1/2 mv squared, where m is the mass of the bullet and v is the velocity that I found in that part there. And when I plug those values in, I end up getting a value for energy that is 2,480 joules. The second part I want to consider is what is my energy after the collision, or my final energy. And I can find that by finding the energy of each individual object. But I know both of them are still moving at 10 radians per second. So I'm going to say it's 1/2 I of the rod, omega of the rod squared, plus 1/2 I of the bullet times omega of the bullet squared. All right? So again, and these are again all values that we already knew how to calculate here. 1/2 ml squared is I of the rod, or the rotational inertia of the rod, and then omega of the rod is 10, as is omega of the, I'm sorry, this should say bullet here. Let's correct that. And so what we end up doing is just plugging our values in, and we actually get an extremely small value for this. We get a value of about 4 joules, 4.175 joules. And so to find the energy lost, you would just subtract the final from the initial to get your answer there. So hopefully this was helpful in terms of thinking about conservation of momentum now in a rotational dimension, and also applying a couple of different ideas now in terms of momentum and energy lost, and how we can take an object that has a translational velocity and convert it into rotational value. Thanks.